A black hole is one of the most mysterious phenomena in the universe. Finding one is not easy, as it does not emit light and is therefore practically invisible. However, a black hole can bend light rays. This means that when a black hole is located between us and a distant galaxy, the light from that galaxy will be bent due to the gravitational field of the black hole. This phenomenon is called gravitational lensing, and it also occurs when large masses, such as galaxies or their clusters, bend the light from distant objects. But that's not all black holes can do. Modern research has uncovered a whole arsenal of their extraordinary properties. It turns out they can move almost at the speed of light and exhibit unpredictable behavior. Their first superpower can be called the cosmic tornado. Black holes spin at incredible speeds which can reach up to 84% of the speed of light. For example, the black hole in the galaxy NGC 1365, located 60 million light-years away, has a diameter of 3.2 million kilometers and a mass of several million solar masses. Its rotation bends space and time, creating a blazing vortex of X-ray radiation, gas, and dust. The second superpower of black holes is their ability to merge. It turns out that black holes can form groups, and this happens more often than we previously thought. The largest galaxies are literally littered with black holes, which may have formed from groups of dying binary stars, or compact black holes that merged with each other. The third superpower is the ability to eject matter the size of Jupiter into space. Some of these clumps of matter can be ejected at speeds of up to 22 million kilometers per hour. For example, near the central black hole of our galaxy, Sagittarius A, there might be a star that approaches very close to the black hole every 10,000 years, causing it to extract stellar matter from it. The fourth superpower is the ability to hide the past of galaxies. ALMA radio telescopes have allowed us to look into the structure of a black hole and discover that the asymmetric shape of its dusty torus may indicate a past merger of the galaxy with another galaxy. The fifth superpower of black holes is their incredible speed of matter absorption. For example, the black hole in the bright galaxy P211 absorbs matter at a speed of 100,000 kilometers per second, which is about 30% of the speed of light. And finally, the sixth superpower is the ability to travel through space like a lone wolf. Black holes can be ejected from their galaxies. One such example is the quasar 3C186, located 8 billion light-years away, which is rushing at a speed of 7.6 million kilometers per hour, trying to leave its home galaxy cluster. Astronomers believe that the cause of this movement is gravitational waves formed as a result of the merger of two supermassive black holes. This merger created a powerful shockwave effect, comparable to the simultaneous explosion of 100 million supernovae. As a result, this quasar was literally ejected from its galaxy. The seventh superpower of black holes is theft. Small black holes can steal matter from their larger neighbors. 5 black hole merger events accompanied by gravitational waves have been officially confirmed. One of these mergers is particularly impressive. 2 black holes, whose masses should have been between 10 and 15 solar masses, turned out to be much heavier, over 20 solar masses each. This happened because they stole matter from a supermassive black hole located nearby in the galactic center. The next ability, number 8, is an extra ration. Black holes can use magnetic fields to increase their mass. For example, in the galaxy Cygnus A, located 600 million light-years away, a very strong magnetic field was discovered. This field helps the black hole absorb surrounding matter, creating powerful radio emissions. The ninth ability is stealth. Black holes can hide even in the smallest galaxies. For example, in the galaxy Fornax UCD3, located in the constellation Fornax, there are about 100 million stars. Although this is a small galaxy, it is one of the densest in the universe. The black hole in this galaxy makes up 4% of its total mass, which is a lot compared to other cases. And finally, the 10th superpower is a crushing blow. Recently, a black hole was discovered that formed about 12 billion years ago and absorbs matter at an incredible rate. This black hole absorbs a mass equivalent to 1 solar mass every 2 days. If such a black hole were at the center of our Milky Way, its brightness would be 10 times greater than the full moon, and it would emit so many X-rays that it would be lethal to all living things. Astronomers have also discovered a black hole in the relatively small galaxy SPT 947, located 22 billion light-years from Earth. This black hole has an unusually high mass and absorbs stars along with their planetary systems. This finding has cast doubt on modern theories about the life of galaxies. How could such a massive black hole appear in a relatively small galaxy? And could it completely consume the entire galaxy? Currently, 3 types of black holes are known. The first type is primordial or relic black holes, which formed in the early stages of the universe's development. The second type is stellar mass black holes, which form as a result of the collapse of massive stars. The third type is supermassive black holes, which are located in the centers of galaxies and can have masses up to billions of solar masses. These fascinating facts show how diverse and mysterious black holes are. Do you have any interesting facts about these cosmic objects? Share them. Imagine how black holes can actually grow in mass. One way is through the accretion of matter onto a supermassive black hole. Another theory suggests that such objects form during the collapse of large gas clouds, which turn into relativistic stars with masses of several 100,000 solar masses or even more. These stars become unstable and eventually collapse into black holes. For example, a recently discovered black hole, Holm 15A, has a mass of 310 billion solar masses. This colossal monster is located in the elliptical galaxy, Abell 85 in the constellation Cetus, about 700 million light-years from the Sun. The galaxy is known for having the largest galactic core, which spans about 15,000 light-years. Despite the massive scale of this black hole, the galaxy it resides in is stable, unlike the galaxy SPT 947. Initially, a group of astronomers was searching for ordinary black holes using the Newton and Chandra orbital telescopes, which operate in the X-ray radiation range. The galaxy SPT 947 is quite ordinary, with a stellar mass 44 billion times that of our Sun. For comparison, the Milky Way, which is considered a relatively small spiral galaxy, has a stellar mass of 64 billion solar masses. However, the black hole at the center of SPT 947 has a mass nearly 7 billion times that of the Sun, making it one of the largest black holes in the early universe. This finding contradicts established theories about the growth of black holes in the centers of galaxies, which suggests that the mass of black holes grows at approximately the same rate as their galaxies. The case of SPT 947 shows that the black hole grew much faster than the rest of the galaxy, absorbing almost all the gas, stars, and resources within the galaxy and in the intergalactic medium. And here's another peculiarity. The black hole in SPT 947 has already reached the limit of its growth, but new stars continue to be born in the surrounding galaxy. This contradicts theories that suggest the radiation from black holes and surrounding gas flows should prevent the formation of new stars. These amazing facts show how mysterious and intriguing black holes are. Do you have any interesting facts about these cosmic objects? Share them. Imagine living in a universe with 10 dimensions. String theory proposes such a structure for our world. However, these additional dimensions are so small that we cannot see them. But we can study gravitational waves, which carry information about their origin and the nature of gravity. Moreover, we can even listen to these waves converted into sounds. For example, when two large mass black holes merge, it creates a distinctive signal that can be heard. Gravitational waves are the result of space-time curvature under the influence of massive objects. And while the existence of the hypothetical particle graviton has yet to be experimentally confirmed, gravity undoubtedly exists. We feel its effects every day. Gravity plays a crucial role in the formation of celestial bodies. It gathers dust and gas to form stars, planets, and galaxies. Gravity keeps our planet and other bodies in the solar system in their orbits, ensuring the optimal distance of Earth from the Sun to support life. It also causes the tides in our oceans due to the interaction between the Earth, the Moon, and the Sun. Gravity holds galaxies and their clusters together, preventing them from drifting apart into space. Studying gravity can help us understand the mysterious dark matter, a form of matter that doesn't interact with light but has a gravitational effect on visible matter. Calculations of galaxy rotation curves show that there is more matter in the universe than we can see, and this excess mass is likely made up of dark matter. Thanks to technological advancements, we now have new tools to study gravitational waves, which help us better understand gravity and our place in the cosmos. Gravity also causes the bending of light around massive objects, as well described by Einstein's general theory of relativity. One of the most interesting effects is gravitational lensing. When light from a distant object, such as a quasar, passes through a massive object like a galaxy, it gets bent. This is similar to how a regular lens bends light, magnifying the image of the object. In some cases, the light forms a ring around the galaxy, known as an Einstein ring. Thus, studying gravity helps us better understand not only our universe, but also the laws that govern it. Every time we look at the stars and galaxies, we observe the influence of this mysterious force. Let's consider another fascinating astronomical phenomenon related to gravity and light, the Einstein cross. Its formation is similar to what we discussed, but there's one difference. The light from a distant object passes through a spiral galaxy, forming a figure that resembles a cross. In summary, modern science suggests that attractive forces as such do not exist. There is only the curvature of space-time, and light travels in a straight line in this curved space, as if it is being drawn towards mass. Light shows us how time is curved, slightly near planets, strongly near stars, and very strongly near black holes, where even light cannot escape their gravitational field. It may seem like light is being pulled, but it actually remains weightless. The laws of our world are such that every body curves its surroundings. Who knows, perhaps in 100 years we will witness even more precise and exciting discoveries that better explain the behavior of light and other phenomena in the universe. Today we use the laws discovered by Isaac Newton and confirmed by other scientists. As early as 1795, the prominent mathematician, physicist, and astronomer Pierre-Simon Laplace hypothesized the existence of invisible stars based on Newton's law of universal gravitation. He predicted that a star with the density of Earth, but 250 times larger than the Sun, would not allow any light ray to reach our planet due to its gravity. For many years, scientists only studied black holes theoretically, and it wasn't until April 10, 2019, that astronomers captured the first image of a black hole as part of an international project. This was an incredible achievement since black holes cast only small and difficult to observe shadows. By combining the power of 8 radio telescopes worldwide, focused on the center of galaxy M87, scientists obtained this historic image. Recently, a new photo of a black hole shadow in polarized light was published, showing twisted magnetic fields, helping astronomers better understand its physics. A black hole is truly a mysterious and fascinating object, about which we know only a fraction of the information. Visually, it is not a hole or a tunnel, but rather a black sphere hanging in space. The closer we get to a black hole, the more noticeable the distortions of space-time become. Imagine the familiar universe beginning to change as we approach a black hole. Space becomes incredibly warped, and time flows differently. Thus, gravity not only warps space and time, but also forces us to reconsider our notions of the universe and its laws. Studying these phenomena helps us better understand our world and our place in it. And it also offers hope for new discoveries in the future. All right, at this point we have reached the photon ring, the region around a black hole where light orbits. This is a place where gravity is so strong that light cannot escape and moves in a closed loop. Behind us we can still see the universe, its light, and even ourselves, as if we are wrapped around the black hole's orbit. This is, of course, an optical illusion created by the warping of space. We will observe as space gradually narrows and the entire universe's light converges to a single point, changing color from red to blue due to the Doppler effect. But in reality, at this stage, we are already gone, disintegrated in every sense. Yet let's imagine we are still here, not torn apart, and continue our exploration. Crossing the event horizon, we and our ship are stretched and resemble a cosmic cigar. This phenomenon is called spaghettification, where objects are stretched lengthwise by the powerful tidal forces in the gravitational field. To escape, one would need to identify the singularity point using gravitational sensors and move in the opposite direction. But this is almost impossible because the singularity point seems to be everywhere. Crossing the event horizon, we will see nothing, even if we turn on the most powerful spotlights. Light cannot disperse this absolute darkness. Photons, the particles of light, move along geodesic lines, but inside the black hole, these lines lead to the singularity, which appears to be everywhere. Our super-strong ship becomes useless, as we cannot see or perceive information normally. Gravitational forces and space warping will affect our brain, and we won't be able to comprehend reality. Our imaginary flight has come to an end. This is just a hypothetical journey based on theories that may change with new discoveries. Black holes challenge our understanding of physics, but even in science, imagination has its place. It helps us open our minds to new ideas. Black holes are among the most mysterious objects in the universe. In recent years, scientists have made many discoveries about them, some of which have laid the foundation for future research. Today we will try to look inside them and discuss some amazing phenomena. A black hole has 3 layers: the singularity, the outer event horizon, and the inner event horizon. At the center of a black hole is the singularity, the region where all the mass is compressed to nearly zero volume, creating incredible gravitational force. The outer event horizon is the boundary beyond which matter can still escape. The inner event horizon is the boundary beyond which nothing can escape, not even light, and everything moves toward the center of the black hole. Black holes spin on their axes. When a star collapses, its mass retains its angular momentum, and the rotation speed increases. The rotation of a black hole causes the surrounding spacetime to rotate. This region is called the ergosphere. where various interesting effects occur. The smaller the event horizon of a black hole, the faster it spins. For example, one of the heaviest black holes, GRS 1915+105, located in our Milky Way galaxy about 40,000 light-years away, spins at a rate of 150 times per second. And in the galaxy NGC 1365, there is a black hole that spins at 84% of the speed of light. It has reached the cosmic speed limit and cannot spin faster due to the strong gravitational field. A black hole not only rotates but also warps the spacetime around it. According to Einstein's theory of relativity, the closer you get to a black hole, the slower time flows. As it spins, a black hole creates an interesting effect called frame dragging, where space and time around it are pulled along with it. This effect was confirmed almost 100 years after it was predicted, thanks to complex analyses of spacecraft data in Earth's orbit. Even Earth, albeit very slowly, causes frame dragging with its rotation, subtly altering the orbits of satellites. To better understand this effect, let's transport ourselves 8,000 light-years away to the constellation Cygnus, where an unusual black hole known as V404 Cygni is located. This is a binary system where a black hole about 10 times the mass of the Sun interacts with a companion star, a red giant. Astronomers noticed a strange phenomenon in this pair. Relativistic jets change their direction within just a few seconds. During this process, clouds of plasma are formed and ejected into space at high speeds. The star's material orbits the black hole, forming an accretion disk with incredibly hot and luminous edges. As the black hole feeds, it emits plasma jets from its poles. The jets of V404 Cygni change their orientation at speeds up to 60% of the speed of light. Scientists believe the black hole's accretion disk is slightly tilted, and the inner part of the disk wobbles and rotates, altering the jet's orientation, similar to a spinning top. This frame-dragging effect pulls on the distorted part of the disk, affecting the black hole's rotation. To observe these effects, researchers took 103 images with exposures of just 70 seconds and combined them, allowing them to see the black hole's jets. But can we hear a black hole? At first glance, space seems silent. However, some sounds do propagate in the universe, though they can only be detected with special equipment. For example, infrasound from a supermassive black hole in the Perseus cluster, located 250 million light-years from Earth. This sound has a frequency that the human ear cannot detect, as it is far below our hearing threshold. Black holes remain some of the most mysterious objects in the universe. We know little about their internal structure since the laws of physics seem to break down at the event horizon, and gravity becomes infinite at the singularity. But science is gradually unraveling these mysteries. In 2019, the European Southern Observatory made a significant discovery: the first direct image of a supermassive black hole. This allowed scientists to study the polarization of light near the black hole in the M87 galaxy and learn more about the accretion disk and jets emitted by the black hole. This discovery helps us better understand how black holes grow and interact with their galaxies. Magnetic fields play an important role in this process, and new data has shown that they can influence the movement of gas around the black hole. Although there is still much we do not know, each new discovery brings us closer to understanding these enigmatic cosmic objects.